And welcome back, everyone, to History of Mathematics. We're going to continue our work through Chapter 12 of Stuart Hollingdale's book, Makers of Mathematics, focusing on the contributions of Leonhard Euler. Now, in the last video, we talked about Euler's identity, which gives a very important relationship between the exponential function as well as the two fundamental trig functions of sine and cosine. And in that video, we reviewed some very important power series expansions for these functions. So we're going to continue building on that and talk about Euler's work on the so-called Basel problem, which involves finding the sum of a specific infinite series. So let's switch over to the document camera and see how Euler did that problem. So from our work with calculus, we know that this series converges. There's a couple of tests you could do that will confirm this. You could use the integral test and integrate the function 1 over x squared from 1 to infinity and see that that is a finite improper integral, and that'll tell you the series converges. You could also use the p-test. So either way, we get that the series converges. Those tests do not, however, tell us what the series converges to. In other words, from those tests alone, we have no idea of the value that this expression would get closer and closer to as the number of terms we add up goes to infinity. Now, Leonhard Euler had a rather ingenious way to figure out what the sum of this series should be. So to review, we are going to talk about the Maclaurin series for sine x. You'll remember it's an alternating series. First term is positive, next term is negative, back to positive, back to negative. So it's an alternating series, and the series contains only odd powers of x. If you review your trigonometry, you might see sine called an odd function, and the reason the terms even function and odd function are what they are relate back to power series. An odd function would have only odd exponents in its power series. An even function would have only even exponents in its power series. Okay, and I also want to review the connection between factors and roots. So I want you to think back to your algebra here. If you know the roots or the zeros of a polynomial function, then you know the factors, and vice versa. So if these are roots of my polynomial, then these have to be the factors. I'm allowed to have a constant multiple out here if I want. I guess equivalently, I could look at factors like this. We usually don't do this in algebra, but this is the way Euler did it, and he had a very specific reason that we'll talk about in just a sec. So in other words, if I plug in R1 for x, this factor would vanish, and we would get a 0. Same thing with R2 and R3. So this is an equivalent way to write down a factorization for our function that has these roots. So Euler's reasoning goes as follows. He says, okay, I know the roots of the sine function. The sine function has roots at 0 and plus and minus pi and plus and minus 2 pi and so forth and so on. In other words, integer multiples of pi. So Euler gets a factorization for the sine function, right? There's the factor corresponding to the root 0. And I guess you could say this is two factors, but they've been multiplied together. Okay, so if I wrote the factor for pi, it would be 1 minus x over pi. And if I wrote the factor associated with negative pi, it would be 1 plus x over pi. If you multiply those out, you'll get this right here, and so on down the line. So you get this. All right. So here's what Euler does. He does this right here. He says, okay, well, let's get rid of that factor of x that's over here. It's not really going to help us. Let's multiply this whole thing out. Let's multiply this infinite polynomial out, because we have an infinite number of factors here. Okay, so, and let me just go in stages. Let me take the first two, multiply the first two. Okay, well, if I do first times first, I get 1, then a minus x squared over pi squared minus x squared over 2 pi squared, and then I guess I would get a plus x to the 4th over, let me just write it like this, pi squared 2 pi squared. Okay, and then of course I still have that next factor sitting out there, 1 minus x squared 3 pi squared. And of course I have infinitely many factors over there that I haven't written. Okay. Now if I bring this through here, I would still get a 1, so I'd get all of those again. Then I'd get another term that involves x squared, 2 more terms that involve x to the 4th, and then finally I'd get a term that involves x to the 6th. Okay, now let me write down some stuff here. Constant term would still be a 1. Now I claim I would get something like this right here. Okay. So let's imagine I multiplied this whole thing out, all the terms. Okay. Every time I come through, I would get another factor that involved x squared. So I'm going to collect all the terms that have x squared. And if I look right here, there's a minus in front of all of them, because every term that involves x squared is going to come from taking this and distributing it through and hitting that 1. And then when you do the rest of the terms, you get higher powers. So that's not going to affect the coefficient of x squared anymore. Okay, so they'd all have a minus. And look right here. You have 1 over pi squared, and then 1 over 2 pi squared, and 1 over 3 pi squared from this next term. So they would all involve a pi squared, so we're going to take that out. And this is the remaining factor for each of them. Okay, we took out the minus sign. This is giving us the 1, 2 squared. This guy would give us the 3 squared. The next factor would have given us a 4 squared, and so forth and so on. Okay. So we've got actually now 2 series. Imagine we kind of continued this. We'd get another infinite series, and all the coefficients would themselves be infinite series. So let's compare the 2 series. From our power series, we would see that sine x over x would be 1 minus x squared over 3 factorial plus x power 4 over 5 factorial minus x power 6 over 7 factorial plus, it would keep on going like that forever. And the series that we got from that product says that sine x over x could also be expressed as 1, and then there's going to be some stuff that involves x squared, and you remember each one had a pi squared, and it would be 1 plus 1 over 2 squared plus 1 over 3 squared plus, and that series would keep on going forever. And then we'd have all the higher order terms over here, terms that involve x to the fourth and so forth and so on down the line. Okay, now Euler's reasoning goes like this. Okay, if these two expressions on the right are both equal to sine x over x, they must be equal to each other. Okay, and that means the coefficients of the various powers of x must be equal. That's the only way for two polynomial functions to be identically equal, is the coefficients of the corresponding powers of x are equal. Okay, so we've got to have this situation going on right here. The coefficient of x right there, now they're both minuses, so I can just disregard that. So 1 over 3 factorial would have to be equal to 1 plus 1 over 2 squared plus 1 over 3 squared plus, that would continue forever, times 1 over pi squared. And that is equivalent to saying that this series, n equals 1 to infinity of 1 over n squared, which is what we've got right here, that this is equal to pi squared over 3 factorial, which is, of course, 6. Okay, so through this process, Euler determines that the sum of this series has to be equal to pi squared over 6. So it's kind of an ingenious method of looking at a function two different ways and then equating the coefficients of the various powers of x. So using processes like that, Euler was able to find values for sums of actually a whole class of series. He was able to do the sum of n equals 1 to infinity of 1 over n to the p whenever p was an even integer. So in other words, 1 over n squared, 1 over n to the fourth, 1 over n to the sixth. He was able to do really that whole class of problems. Okay, and we're going to continue in the next video to talk about Euler's work, but no longer are we going to be talking about analysis. In other words, we're not going to be dealing with infinite series anymore. We're going to be dealing with a branch of mathematics called graph theory. So we'll link right down there to Euler's work on graph theory for our next video.